Okay, and welcome to part three. Part three now? Yes, part three of our introduction to hydrocarbons. So, hopefully, when you were looking at the structural formula in the last video of some of our alkanes, you noticed that there was a little asterisk next to hexane and butane and pentane. And that little asterisk actually meant that, and maybe you figured this out already, especially if you've been using the model kits, that there are more than one way for us to put those together. Okay, so remember how we said that isotopes were different forms of the same element when we had different numbers of neutrons? Well, isomers, okay, so this one here, isomers, are different structures of the same molecular formula. So they're molecules that have the same molecular formula but different arrangements of atoms. Okay, so in the case I said that hexane was one of them, and hexane is our C6H 12, 14, okay, and hopefully when you drew it out, you drew out 1, 2, 3, 4, 5, 6, and then some hydrogens coming off it. Some hydrogens coming off it here. Okay, so this is hexane. But if you think about this, there are many, many different ways that we can put together C6H14. They don't have to be in this straight chain all the time. I could take one of these off and put it onto here. In fact, if you are actually watching this video at school, I highly recommend you get a model kit now and you build hexane so that you can have a look at the different ways that we can put it together as we go through this. Okay, so alkanes and alkenes, which we're going to do soon, that have less than 4 carbon atoms per molecule, there's only one way we can put them together. So if we think about propane, okay, which is 3 carbons, there's no other way I can really put this one together. These 3 carbons just all have to go together. I can't sort of move, if I try and move this one off and put it over here, I'll just end up recreating their original molecule. So if they're 3 carbons and under, there's pretty much only one way we can put them together. So they have only one isomer. Okay, but if we look at butane, which is 4 carbons, onwards, okay, then it can have multiple arrangements. Okay, these compounds can have we could have 2 carbons, a CH3 coming off it. We can put them together in a whole bunch of different ways. They will still have the same molecular formula though. They'll still all be 4 carbons and 10 hydrogens, or 5 carbons and 12 hydrogens. Okay, the only way that they differ will be by this different structural formula. Interestingly, because they have all the same kinds of bonds, we're still going to keep all the bonds single and everything like that. The chemical properties are pretty much the same, and the physical properties depend on how sort of branched and open up the structures are. And if you think back to dispersion forces, that makes sense because we talked about them needing to get nice and close together. So let's look at some isomers. Isomers of a molecule basically have similar chemical properties but not identical, and as the chain length increases there are a greater number of possible isomers. If we look at butane here, I've got carbon 1, carbon 2, carbon 3, and carbon 4, okay, all with the hydrogens coming off them. And this is what we call a straight chain isomer. Okay, and then this is still butane because if we have a look, we've got 1 carbon, 2 carbons, 3 carbons, but then I've got this other carbon up here as well, so that gives me 4 carbons, and then I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens, and butane of course is C4H10 if you remember back to your original table. So that is what we mean by an isomer. Different ways of putting them together. We've taken one of these, we've actually taken one of these carbons. Oops. We've actually taken one of these carbons here, pulled it off, and put it on to this one over here. so that we form this isomer here. So what I want you to do is have a go at building the different isomers of hexane. Particularly this should be your double period now, so have a go at building them, see how many you can find. Okay, so stop the video, build yourself a H14 molecule and have a go at building all the different isomers and see how many you can find. Once you've had a go at that, come back and watch the rest of the video. If you have been on cadet camp and you don't have a model kit with you, have a go at drawing them on a piece of paper and see how many you can come up with. And then come back and I will draw them all out for you. Okay, hopefully you have either built or had a go at drawing these for yourself. And let's see if I can draw them on my computer without swapping the slide too much. So let's go. First isomer is going to be straight chain. I'm probably going to be a little bit lazy since I'm drawing on my computer and not drawing all my hydrogens. But we've got 1, 2, 3, 4, 5, 6, and then we've got, these will have hydrogens. Oh, keep sliding, sorry guys, off each of these positions here. So that's 1. Okay, 2. So what happens if I grab this guy here? I'm going to grab this guy here and I'm going to put him on one of these ones. So 1, 2, 3, 4, 5, and I'm going to put it on this one here this time. Okay. Hopefully you realized if you built this, if I put this one on this carbon over here, I'll actually be making exactly the same molecule because it can flip and rotate in three-dimensional space. So the next one is actually going to be if we, okay, oops, got 6, I only need 5. Okay, so I put it on this one last time. So this time I'm going to put it on this one in the middle here. And that will have a hydrogen atom there as well. Okay, so that's 3, but I can still put this together in a few different ways. So let's see. I'm going to pull off another one and I'm going to make my chain 4 long. And then I'm going to put a branch here and a branch here. Okay, so now I have these 2 branches, but can I put it together in another way again? I think I can. Let's have a look at number 5. If I, 1, 2, 3, 4, if I put both of them off this one here, I get something else again, and then I could also, can I do another one? I think we're done. I can bring this one over to here. Maybe. Nope. I think we're pretty much done. So these are our isomers of hexane. If I've mixed one, let me know. I'm usually pretty good, but I'm a little bit tired tonight, so maybe I missed one. Okay, so as you can see here, I can get a lot of different isomers. Key thing, there is no formula to work out the number of isomers. Okay, it's just, there's no magical number. There's no relationship between the number of isomers that we will see if we've got C6 or if we have C7 or C10. There's no progression or linear progression in that. You've just got to start moving things around and draw them out until you think you've found them all. Usually you won't be asked to draw more than about 5. In an exam you might be asked to draw 3 or 4. But you need to know how to draw isomers for all of them up until heptane, which is C7. So have a go at drawing all the isomers for heptane. I'm sure if you Google isomers for heptane, you'll get to check and see how many you've got and if you've gotten them all right. Okay, so key thing here, these are all covalent molecules. They're non-polar. Okay, so they're non-polar covalent molecules. Because they're non-polar, the only intermolecular force that we see between them is, of course, dispersion forces. So bonding between the carbon atoms in the chain is covalent. Overall, the molecules are non-polar, and it means that the intermolecular forces between molecules will be weak dispersion forces. Okay, let's move on. So essentially, hopefully you remember from covalent bonding, with weak dispersion forces, the strength of the forces increases as the size of the molecule increases. So larger molecules have stronger dispersion forces, higher melting points and boiling points. Okay, and the smaller the compound, the more volatile. And volatile is when we're talking about turning into a gas. Okay, so if it's highly volatile, it turns into a gas quite readily, and less viscous. Viscous is a measure of how much something flows. So if you think about honey, honey is a very viscous liquid. It gets less viscous as we heat it up. Okay, and we talked about branching and how much things could hold together and distance dependence when we talked about dispersion forces with covalent. This comes into its own really when we're talking about hydrocarbons, and this is these two diagrams give us a good example. Okay, if we look at this, if we have those straight chain isomers like with hexane where we draw them all out like this, okay, that means that they sort of can stack really nice and close together. They have a really high surface area, which means that when those dispersion forces, those instantaneous dipoles occur, there's a wide surface area for them to attract with each other. As we increase the branching in our isomers, we get these little fractally bits that come off the edges of them. Basically, that reduces the surface area, so it reduces the strength of our boiling point, strength of our dispersion forces. So our branched isomers, okay, so our branched isomers will have lower boiling points and melting points compared to our straight chain form. So if this is our hexane in the straight chain form, 1, 2, 3, 4, 5. Okay, so if we had our branched form here, which is 2,3-dimethylbutane, it would have a lower melting point because these branches mean that we have lower surface area. I want you to have a think about what that means for our viscosity and our melting points, which are also based on the strength of our dispersion forces or intermolecular forces. Okay, that's it for melting points and boiling points. We have covered isomers, and we've also covered alkanes at this stage up to C7. I'll do one more video, but I think that'll be enough for you to go through and work on this week. So you should go through, read your textbook, do the questions, and have a practice at drawing out your structural formulas. Have a go at drawing all your isomers for hexane and heptane as well. Okay, and then move on to the next video, which will be on naming.